if we continue on a bit, then we come up to experimental probability. So your books use the term experimental probability versus the theoretical probability. So essentially what this means is we are going to run an experiment a lot of times to see if our results match what we think the results must be. So if we take a dice, a 6-sided dice, and we want to see if this dice is fair, so it's not a loaded dice. Say a casino wants to see, this dice is fair. It's going to come up on every probability equally. It's not just going to come up on 6s the whole time. Something like that. Then you have your theoretical values over here. So say we want to roll 60 times. So then theoretically, each of these should be 1 in 6. So each of these should be, we should get 10 times, right? But experimentally, we take this dice and we physically roll it 60 times. I did this earlier today. It took a while. Then we can get different values. They're not quite 10. So we've got 1 came up 11 times, 2 came up 7 times, 3 came up 10 times, 4 came up 13 times, 5 8 times, and 6 11 times. So would you say this dice is fair? Or would you say this dice is not fair? Because they don't quite match up. But actually this dice is fair. And the reason is these are not very far away. If this was a 5 or a 4, then I might be worried. But it's not. This is a fairly fair dice. They're within sort of 5 of 10 because we didn't roll the dice very many times. If we instead go and we roll this dice 1,000 times, what are we going to get there? So I'll show you that in a minute. So if a dice is fair, then the more times we roll it, the closer it should look to the theoretical values. So instead of just 60 times, we rolled it 6,000 times. Then we should get about 1,000 in each. So let me go show you guys. So here we go. That one. So this, I hope you guys can see this, is essentially a dice rolling app online. So I will give you the link. It's academia.org/demos dice roll statistics. So we've got a single 6-sided die here, and we have rolled it a bunch of times. I've already rolled it 500 times. As we continue rolling, you can see that these are climbing slowly. There's now more than 100 rolls of each, except for maybe this one. So as we continue on, you'll see that these stay more or less equal, right? They're not too far off. This one is maybe a smidge low, but no, they're not too far off. So as we continue rolling, you'll see that they start to even out. They start to look pretty much the same in terms of length. So I'm going to refresh this page so that we can start again. So now we've only had one roll and it came up as a 6. So as we start rolling the dice a bunch of times, you can see that here, as we have very few rolls, they look fairly erratic. But as you saw with the previous one, as we continue on and we get more and more and more rolls, then they actually start to look a bit better. Here, we've had like 180 rolls and it's looking like this dice is very unfair. It looks like we have a lot more 6s than we have any of the other numbers. So in statistics, we need to test something a bunch of times, or we need to have a bunch of different people that we test something on before we can say, oh, it actually, yes, it works. So I'm just going to stop that so that it doesn't take up everything. So there we have a bit of an idea of all of the many times we have to roll a dice. So in statistics, if we want to test something, you have to test it on a bunch of different things. You either have to roll your dice a bunch of different times, 1,000 times, just very, very much. Or if you have, say, a new drug, a new kind of medicine that people want to test, then you need to get lots of people that have this specific kind of illness, and then you need to give them this drug to see if it actually works. There, they do something called double-blind testing, which means they test them on the people, and then they also give some of the people a placebo to see whether doing nothing is actually better than giving them the medicine in the first place. So, kind of strange. But here we go. Let us continue. So that is the difference between theoretical and experimental probabilities. Now we get to continue on with a bit of actual statistics. So if we are rolling a 6-sided die, that is literally a normal dice that you guys use for your board games, for things like that. It's a normal 6-sided die. So what is the probability of rolling a 2 on a 6-sided die? Excuse my terrible spelling over there. So we can write down all of the different ways that we can get an outcome on the dice. We can roll a 1, a 2, a 3, a 4, a 5, or a 6. So what is the possibility of rolling a 2? There it is. Okay. Now, if we want the probability of rolling a 2, then we need the amount of 2s over the total amount. Okay. So the amount of 2s there is 1, 2, and our total amount there is 1, 2, 3, 4, 5, 6, 6 different outcomes. So our possibility of rolling a 2 is a 6. Okay. So what is the probability of rolling an even number on a die? So let's go write out all of our possibilities that we can get on this die. And now we want an even number. So that's a 2, a 4, or a 6. So our probability of getting an even number is then 1, 2, 3 out of our possible 6 different outcomes. Okay. What is the probability of rolling a 3 or higher? So now we have 1, 2, 3, 4, 5, 6. So we want a 3 or higher. So that's that, or that. So our probability of rolling a 3 or higher will then be 4 of the ones that work over our 6 possible outcomes. So that is a 6-sided die. And you guys have probably looked at a 6-sided die fairly often. So now we're going to do something a little bit stranger. We're going to look at one of these 20-sided die. So just to be clear, this is what a 20-sided die looks like that. And it literally has 20 different sides that we can roll, if I don't drop it. It's okay, I'll find that one later. I've got tons. So there are literally 20 different sides to it. So we can roll 20 different numbers. We can roll anything from 1 all the way up to 20. So let's continue. So what is the probability of rolling a 20 on a 20-sided die? So we can write out all the numbers 1, 2, 3, all the way up to 20, and do exactly the same as we did with a 6-sided die up top over here. But it's going to take a little while. So this time we're going to be thinking of the thing slightly mentally. Okay. So what is the probability of rolling a 20? So we've got the probability of rolling a 20 will then be the amount of 20s on the die. So we've got 120 on the sides of the die, and then the amount of different outcomes we can get. So that is 20 different outcomes. So our probability is 1 over 20. Okay, what is the probability of rolling an even number? So all of the even numbers will be 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. 10 different even numbers. Great. So our probability of getting an even number will be 10 outcomes out of our possible 20 outcomes. So it's a half. Okay. So what is the probability of rolling a 12 or higher on our 20-sided dice? So this time I'm going to write them out. We've got 1, 2, 3, 4, 5, 6, 7, 8. Here we go. And 20. Okay, so we want a 12 or higher. So there's a 12, and these are all higher. Okay, so now we can go count the amount of outcomes. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So our probability of rolling a 12 or higher is then 9 out of 20. Okay. So that is how we can use different kinds of dice. The same thing for dice counts for spinners. If you have spinners that have a certain amount of numbers and things, this is the way you use it. So now we continue on with something slightly different. So drawing things from bags. So we have the letters of the word Mississippi. So there is 1 M, 4 I's, 4 S's, and 2 P's. And we write them all on cards and we put them in a bag. So now our probabilities are no longer equal. When we roll the dice, we can get a 1, a 2, a 3, a 4, a 5, or a 6, right? But there wasn't two different ways of getting one of the numbers. So here, we now have different probabilities. So this works slightly differently. So what is the probability of drawing a P? So we have the probability of drawing a P. So now we go count the amount of P's we've got. We've got 2 P's. And we have how many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 letters. So our probability of drawing a P will be 2 out of 11. What is the probability of drawing a vowel? So we look at Mississippi. There are 1, 2, 3, 4 vowels. So the probability of getting a vowel will be 4 out of 11. Okay. So what's the probability of drawing a consonant? So consonants are the opposite of vowels. So essentially what we're trying to ask is what is the probability of drawing not a vowel? So that we can use that formula for. So that is 1 minus the probability of drawing a vowel, which gives us 1 minus 4 over 11, which is 7 over 11. Okay. So continuing on, probability of drawing an S. So we need to go back up here and go look at how many S's there are. There are 4 S's. So that would just be 4 out of 11. And the probability of drawing an M, there is literally only 1 M. So probability of drawing an M will then be 1 out of 11. Okay, so now we get to marbles. So similarly to the previous one where we had multiples of a letter, now we have multiples of a colored marble. So we put some colored marbles in a bag. There's 1 black marble, 2 white ones, 3 yellows, 4 greens, and 5 blues. Okay, so let's go draw a little table. If I can actually draw a straight line, that would be great. So we start with black. Then we have white, yellow, green, and blue. The only reason why those 2 are written out is because they start with the same letter. Great. So there we have a little table. So now we can go write down exactly what kind of marbles we have. We have 1 black marble. We have 2 white ones, 3 yellow ones, 4 green ones, and 5 blue ones. So our total number of marbles is 1 plus 2 plus 3 plus 4 plus 5. That will give us 15. So what is the probability that you will draw a black marble? So the probability of black will then be 1 out of 15. Okay, what is the probability that you will draw a blue marble? Probability of blue, you'll need to know it's going to be out of 15, but there are 5 blues. So that's our answer. We can go simplify it and say that'll be 1 over 3. So what is the probability that you will draw a yellow or a green marble? Okay, here it gets slightly more difficult, because if we draw a yellow marble, it's fine, and if we draw a green marble, it's fine. So we need to add these two probabilities together. So we've got 3 yellows and 4 greens. So if we draw either a yellow or a green, there are 7 different possibilities out of our 15 total. So probability of yellow or green will then be the 3 from the yellow plus the 4 from the green, all out of 15. So we've got 7 out of 15 different possibilities that we can get either a yellow or a green. So what is the probability that you won't draw a white or black marble? So we have 2 white marbles and 1 black marble. If we go look up here, 2 white, 1 black. So our probability of drawing white or black is then equal to 1 plus 2 over 15. So we have 3 over 15. So now our probability of not white or black, I'm not going to write it out, 15, there we go, is then 1 minus 3 over 15. So we get 12 over 15. Okay, so if we go look up here and we add up all of the ones that are not black or white, so we've got 3 plus 4, that gives us 7, plus 5 gives us 12. We get to the same answer. So this is essentially how you end up doing probability using all sorts of different things. There is one slight trick to this. Okay, if you have only 2 outcomes, it does not necessarily mean that those outcomes are equal. Here's an example. I can say that all cars in the world are either Volkswagens or they're not Volkswagens. So what is the probability of a car being a Volkswagen? If you think about it that way, and you try and treat it like a normal dice problem, then you're going to be wrong. Because then you're going to say, no, half of the cars therefore have to be Volkswagens, but that's not true. In the world, there are lots of other different car makes that are not Volkswagens. So you can't just say that because we've only got 2 outcomes, the probability then has to be half. So if you know every single outcome, like the way that we did in the drawing marbles out of a bag, all of the numbers on the dice, we know what all of these outcomes are. We know that you can roll a 6. We know exactly how many possibilities there are of rolling a 6. Then we can do statistics with it. If we have a bunch of marbles in the bag, then we know exactly which kinds of marbles and of what colors. So we can do some statistics with it. In terms of how many cars are Volkswagens and how many cars are not Volkswagens, we don't necessarily know in the world how many Volkswagens there are and how many not. So in the end, we're going to have to do some actual research, get some statistics, maybe ask a bunch of people whether they drive a Volkswagen in order to start guessing and saying, okay, I think about 10% of the cars out there is Volkswagens or something. Okay, so that is my lesson for today.